this afternoon session. Today's first talk is going to be by Bar-Natan from University of Toronto on cars, interchanges, traffic counters, and a pretty darn good knot in there. So over yours.
Okay. Hello, everybody. Thank you for inviting me to Geneva. I'll be talking about cars, interchanges, traffic counters, and a pretty darn good not invariant. And I will be reporting on joint work with Roland van der Veen, who is over there. And it continues work by Rosansky and Overbay. So the invariant is the same invariance, but the formulas are different and the context is different. And basically, I'm going to tell you that a certain invariant rho 1 is very easy to define, and I think I take pride in that because sort of the easier something is, the better. And strong and fast to compute and homomorphic, and I'll have to explain what that means, and is well connected to other parts of mathematics. And as I said before, you should all be holding a handout. Here's what it looks like in full glory. And I should also say that omega epsilon beta stands for http://drawbn.net/J22. And the handout and everything else is available there. And in particular, if you go to omega epsilon beta/APAI, it will take you to a paper on the same subject that Roland and I posted on the archive just a few days ago. So it's, everything is in writing. But before I really start, a few pictures I took of Vaughn, whom we miss dearly. So this is Vaughn in his office in Berkeley. This is Vaughn's eye in Maui. But you can see Hugh Woodin's brother here, I forgot his name, and Dylan Thurston over here. And this is Vaughn in Jerusalem giving a talk. And here he is in the Dead Sea, and in Qumran in the Judea desert, and finally in Switzerland in Lake Thun in, I think it was 2011. And if you want more pictures or the same pictures at higher resolution, you can go to omega epsilon beta/J. And let me start. So we seek strong, fast, homomorphic, not entangle invariants. So let me explain all of these words. Strong means having, well, good at separating knots. Basically, having a small kernel. That's kind of obvious. Fast means, so you see, in practice, well, many knot invariants are, well, the formulas are end up being exponential time to compute, which means that you cannot compute them on large knots. But some of the knots we care about, in particular, well, here is a knot by Lisa Picirillo that people care about. And here is a knot by Gompf, Scharman, and Thompson, which might be a counterexample to the slice equals ribbon conjecture. So people care about such knots, and this is a pretty big knot. It's 48 crossings. So I want invariants that you can compute quickly, so you could compute them even for reasonably large knots, and of course the best is if it's polynomial time to compute. And finally, I want to explain what's homomorphic, and I'll be a little bit loose about it because I will not have much time to really talk about it. But homomorphic means it should extend to tangles. So tangles are like a piece of a knot, like here, so half a knot drawn inside half of the plane. Okay? So it should extend to tangles, and it should behave well under tangle operations. So what are tangle operations? Well, first of all, if you have two tangles, one drawn on this hand and one drawn on that hand, you can put the two hands side by side. Maybe you should match the fingers. And then you get a bigger tangle. So to be homomorphic would mean that if you can compute the invariant of this and the invariant of that, you can compute the invariant of the union. And more interestingly, what have I done wrong? Oh, I'm
Nothing.
too loud. Okay. Or more interestingly, so if you have a tangle, then there are a few extra operations. So for example, let's say the strands are numbered, I don't know how. Let's say this one is number 1. Then there is the operation called D1, which means double strands number 1, and the picture makes clear what it is. And likewise, there is an operation, call it S1, for switch number 1, so reverse it. So I want the invariants that have the properties that if you know the invariant of the left-hand side, you also know the invariant of the right-hand side. By the way, the Kaufman bracket doesn't have this property. It's not an obvious property. Okay? So why care for this property? So here's a little theorem. So a knot is ribbon. So if you don't know what are ribbon knots, it actually doesn't really matter. You can use this as the definition of a ribbon knot. Okay? But let me just say that ribbon knots are interesting in topology, and there are open questions about them. Okay? So a knot is ribbon if and only if there exists a 2n component tangle T with skeleton as below. So here is T. And what I mean by having the skeleton as here is that, well, the leftmost strand goes from top to bottom, the second one goes from top to top, and so on. But inside they could be knotted. I'm just not drawing it. Okay, so this could be a whole mess, this T, but I want the connectivity to be as shown. And so a knot is ribbon if and only if there is such a tangle T with the properties that tau of T is equal to the knot K and delta of T is the untangle U. So what are tau and delta? So delta is the operation that drops all the vertical strands, so you're left only with the caps, and you want the result of doing this to be the untangle, so to be the untangled union of caps. And tau is a more complicated operation, so you double each of the vertical strands, and then you attach a tangle as shown at the top, and another one as shown at the bottom, and that gives you a knot. And the claim is that this is precisely the collection of all ribbon knots. Why should you care? Because I've just given you an algebraic definition of ribbon knots within the class of all knots, given some algebraic operation, or given some operation, tau and delta, and these operations are compositions of the operations that my invariant is supposed to be respecting. So the operations with respect to which I demanded homomorphicity. Now, if you look at it, it means that the invariant of a ribbon knot, if the invariant is homomorphic, then the value of the invariant on a ribbon knot will be constrained to lie in some subset which is defined by the algebraic analog of this condition. And this means that in principle, you may have a criterion for showing that certain knots are not ribbon, and that would be interesting. So I'm only sketching it, and if you want to hear more, you can go to omega epsilon beta / AKT, where it's fully explained. But I just want to say there is a reason why I care about homomorphic invariants. They can be useful.
What is the smallest non-ribbon knot?
The trefoil. And the smallest ribonaught is, I think, 6,3 of the prime knots. Anyway, so back to Von Jones swimming, or not quite swimming, floating in the Dead Sea. 20 years ago or so, in about the year maybe 99 or maybe 2000, Dylan and I had an amazing, lovely, beautiful theory. Something about the Chern-Simons measure. If you look at its push forward to various things induced by knotted trivalent graphs, and then there are push forwards, compatible push forwards of measures between them, blah, 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 blah. And we told Von about this, and he said, basically, lovely, but can you write formulas? And then he added and said that sort of formulas stay, but theories, change with the weather, or interpretations change with time. And no, we didn't write formulas, and this great theory is completely vanished, does not exist. Nobody cares about it. Nobody knows anything about it. Following Von, I think I want to start with the formulas and then tell you the stories, cars and interchanges and all that, only later. Okay? So, formulas. So, I want to tell you how to compute this invariant. Okay? So, suppose you have a knot. Well, you draw it upright. What does upright means? It means, well, you draw it as a long knot. It starts at the bottom, ends at the top. All of the crossings are oriented upward. So all the strands are oriented upward. And of course, you can do it, because if it's not how the knot was given to you, well, first of all, you cut it open and you make it look like this. And then if the crossings are wrong, you just turn them around as required. And after that, you label every edge with two labels. So one label is just a running index. So this is edge number 1, this is edge number 2, number 3, this one, the long one, is number 4, then number 5, then number 6, and so on. And secondly, you mark each edge by its rotation number, phi sub k. So edge number k will have a rotation number phi sub k. Now, all the edges by design begin vertical up and end vertical up. So the tangent starts facing north and ends facing north, and then as you go along the edge, you can count how many times it turns around the circle counterclockwise, and that's the rotation number. So here, all of the edges have rotation number 0, 0, 0, except edge number 4, whose rotation number is -1, because it rotates counterclockwise. Okay? And then, having done that, you form a 2n plus 1 by 2n plus 1 matrix A by, you start with the identity matrix, and then for each crossing, you add a 2 by 2 block. So, if you have a crossing C, first of all, it has a sign, which is either +1 or -1. And also, it has two indices associated with it. I, the index of the incoming upper edge. So it's always I. The upper edge is always I. And J, the index of the incoming lower edge. And this, of course, means that after that, there is I plus 1 and J plus 1. And when you see a crossing like that, you add to A in row I and row J, and column I plus 1 and column J plus 1, the following 2 by 2 blocks. 2 by 2 blocks. Negative t to the s minus 1, and 0, where s again is the sign of the crossing. And then you form G. I can't manage this mouse really well. So then you set G to be the inverse of the matrix A. So for example, for the trefoil as shown up there, so I've marked in yellow one of the crossings. So this is a crossing between 3 and 6. So in row 3 and row 6 and at column 4 and column 7, I've added a copy of this block. Okay? And likewise, I continue to create this matrix A. And then I invert this matrix A and call the result G, and I also call the result the green function sometimes. Okay? And here's a picture of green. It was actually pretty hard to find. Everything that I said so far is ancient. So these 2x2 blocks, people will recognize it as basically the Bureau representation. This matrix is a presentation matrix for the Alexander module given by applying Fox calculus to the Wirtinger representation. And the inverse, well, it's not the Blanchfield pairing, but it's related to the Blanchfield pairing. So everything that I said is ancient, and you can tell that it's ancient because all of these pictures are black and white. So, you know, if you were Cameron Gordon, and I'm really sorry he's not here because I really wanted him to be here now, you would yawn because it's so boring. In fact, the determinant of this matrix A that I wrote is essentially the Alexander polynomial, up to a minor normalization. So if you multiply by t to the minus phi minus w divided by 2, where phi is the absolute total rotation number, the sum of all rotation numbers, and w is the sum of all the signs of all the crossings, you get precisely the Alexander polynomial. So boring. Fall asleep, please. Everything that's new is in this box. So, given a crossing, let me remind you, oops, what happened? Oh, I know what happened. Anyway, given a crossing, remember that a crossing is really a triple, a sign S and two integers, I and J, which indicate the upper strand and the lower strand. So, given a crossing, define R1 of C to be the sign S times a certain name, I don't know what to call it, uninteresting, boring, ugly formula. But the good thing I can say about the formula is that it's just quadratic in the entries of G. Okay? So it's a product of some entries of G, and it's just quadratic. Okay? And then define row 1 to be the sum of all of the R1s over all the crossings, and then subtract the correction term, which is a sum over all the edges of the rotation number of the edge times the entry on the diagonal of the green function entry on the diagonal minus a half. Okay? And then you see this was quadratic in the inverse. The inverse will have denominators, the determinant is the Alexander. So this whole thing written inside the parentheses will have denominators, the Alexander squared. So just kill the Alexander, just kill the denominator. So multiplied by delta squared. Okay? And our theorem is that row 1 is a not invariant. And if you are a classical topologist, you should be saying now, what the heck? This is something that you don't do in topology. There is just no precedent. You don't do that. Okay? So where is it coming from? What is it? Okay? So, but you see, I think I took Vaughn's advice that formulas are better than theories to an even higher extreme. I mean, the truth is that I don't care about formulas unless I can implement them and unless the program runs. So here is a complete implementation of the invariant. First of all, I upload some library functions, essentially. So this is meaningless. This is just a list of all the knots. That's all we're going to use. And a little routine that computes rotation numbers. So, I mean, this is something combinatorial to compute, and it's not really a part of the program. So that's all I'm doing for startup. And then here is the full program. So first of all, the first two lines, where is the mouse? Okay. The first two lines define R1 of S and I and J, so R1 of a crossing. Then I define rho of K to be, well, some local variables. And the first thing that I do is I compute the rotation number of K. So this program returns, given any known presentation of K, it will return a list of crossings, each one given as a triple, and the list of rotation number. And I set n to be the length of the list of crossings, so that's just the number of crossings. Then I make the identity matrix of size 2n plus 1. That's exactly what the program is supposed to do. Then within the list of crossings, every time you see an Sij, you do the operation of taking I in rows IA and, taking the matrix A in rows Ij and columns I plus 1 and J plus 1, and you add there the block written here. That's exactly, I'm literally just repeating the definition of the invariant. Then I set delta to be the determinant of A, essentially. I set G to be the inverse of A. And let me tell you on the side that when you execute this program on a very big knot, everything up to here takes 0 time. Computing the inverse of A takes everything, and then the rest also takes 0 time. So basically, the complexity of this is exactly like inverting a matrix. Okay, and then I set rho 1 to be the sum over all crossings of R1 on the crossing, and then the normalization factor. It's really, you don't need to know the syntax of this language. It's clearly a repeat of what I said before, okay? And then you output, so you actually output, you output delta squared times rho 1, in which you replace every G alpha beta by the corresponding matrix entry of the matrix G. And you also output delta, the Alexander polynomial, because really I see delta and rho 1 as inseparable. You compute delta in order to compute rho 1, so they're not really separate entities. And then you output the result factored, and here are some examples. So here is a table of the output for all knots with up to 6 crossings. So for the 5-2, for example, this is the Alexander polynomial, and this is the rho 1. Okay? Then here is a 48 crossing, and now it's fully labeled, and then I type it in. Typing it in takes half a day. You hit enter, and 86 seconds later, you find that the Alexander polynomial is given here, and rho 1 is given by these formulas. Whatever. The point is that it was a 48 crossing knot, and it was fast to compute. Okay? And finally, this is a strong invariant. So we compute the values of the invariant of all knots with between 3 to 12 crossings. We also compute the Homfli-Petit polynomial and Chovanov homology of the same collection of knots, and we count. So there are 2,977 knots. Our rho 1, sorry, it's not our invariant, Rosansky and Overbay gets 2,882 values. Chovanov and Homfli-Petit get 2,785. Rho 1 is stronger. Okay? So we beat everybody here who is in color pictures, with color pictures, except one. Sorry, so I hope you're still with me, because now starts the interpretation. That's the part that Vaughan predicts will evaporate. So I have to tell you a little bit about cars. And in fact, what I have to tell you repeats or is related to an old paper by Lin, Tiang, and Wang, in which they talk about random walks. and an even older paper by Vaughan Jones in which he talks about balls on bowling alleys, but we are talking about cars. So here are traffic rules. So cars always drive forward on a knot, right? A knot has an orientation, so if a car drives along a knot, it always drives with the direction of the edges. When a car crosses under a crossing, it just goes through with no change. When it crosses over a crossing, so when it goes on the upper strand, then with probability 1 minus t to the s, where t is some number close to 1, so with probability close to 0, it falls down, and with probability t to the s, it continues. So, for example, here is a positive crossing. If a car enters here, it will exit with probability t up here, and with probability 1 minus t up here. And maybe I should explain these struts. So these struts are traffic counters. So I'm sure you all know traffic counters, right? Occasionally when you drive, you see a wire, a black wire across the road, and it counts how many cars or bicycles go through. And it's kind of a dual to a car. So, because it counts cars, so the traffic counter placed here will count 1 minus t, and the traffic counter placed here will count t. But however, if you enter the interchange at the bottom, this traffic counter will count 1, and the other one will count 0. Okay? And you can complain that these aren't really probabilities because t and t inverse cannot be numbers between 0 and 1 at the same time. It doesn't really matter. I mean, I'm using probability only in an algebraic way. I will never actually use inequalities. Okay? So let's do, sorry, before the example, here is a lovely picture of the situation made by Roland and his kids. So, but now let's do a theorem. So, the green function, where is the mouse? The green function g alpha beta is the reading of a traffic counter. You put a traffic counter at beta and you inject traffic at alpha, and you just count which fraction of the cars that enter at alpha get to beta or get counted at beta. Okay? And by convention, if alpha is equal to beta, you place the counter after the injection point. So so basically, the counter at alpha will be placed after the point where you inject the cars. Okay? So here is an example. So I inject the car at the beginning, and then the first counter measures 1. Okay, and then the car goes through because it's because it goes under. So this counter here also measures 1. But then the car continues, and with probability 1 minus t, it drops down, and then it gets counted again. So this counter will now count another 1 minus t. And then the car continues, and with probability 1 minus t, it will fall again. So with probability 1 minus t squared, so we'll get an additional contribution to the counting here of 1 minus t squared. And in general, the car might loop around a certain number of times, so the counter here will count the sum over all p, the number of times you went around, 1 minus t to the p, and this is a sum of a geometric series, and it sums to t to the minus 1. Okay? Now, if you inject the car on edge number 1, on edge number 2 instead of edge number 1, then the first counter counts 0, but this counter is unchanged. It's exactly the same looping that happens. And finally, if you inject the car at the very end, then these two counters don't count anything, but the last counter counts 1. So the overall green function matrix will be the matrix written over here. So 1 T inverse 1 for the first row, then 0 T inverse 1, then 0, 0, 1. Okay? Proof. So basically, it's easy to check that near a crossing with sign S and labels I and J, the green function and the car traffic counting, both satisfy these equations written here. So let me explain. So the equation, the second equation, Gj beta is equal to delta J beta plus Gj plus 1 beta, really says that if a car, so if beta is far away, is not equal to J, then it just says that Gj beta is equal to Gj plus 1 beta, which means that if a car is injected at J, it's the same as if it's injected at J plus 1, which is the traffic law that says that when you go under a crossing, nothing happens. Now, however, if the counter is precisely at J, so if the counter is here, then there is a difference of 1 between injecting the car at J or at J plus 1, because the cars injected at J go through this counter over here, but the cars injected at J plus 1 don't go through that counter. So that's the second equation. And similarly, the first equation is the traffic law, the traffic rule that says that if you start at I, you either continue with probability T or drop down with probability 1 minus T. So car traffic obeys these rules. But these rules are also the fact that A times G is equal to 1. If you just read out what the matrix A is, the fact that A times G is equal to 1 is precisely some condition on the columns of that matrix. So, so the two are the same, and so I've proven my theorem. And in fact, there is a bonus to this. And the bonus is there are also rules for moving traffic counters. So you can either deduce them by pure thought, or note that if AG is equal to 1, then GA is also equal to 1, which means that there are rules on the rows of the matrix G, and they are written over here. Okay? So that was a preliminary. And now let me prove invariance to you. So let me start with the hardest, so invariance under Reidemeister 3. Okay? So first of all, let's observe that if you inject a car at the bottom left of a Reidemeister 3 move, either on the left-hand side or on the right-hand side of the move, so the probabilities that it will, or the distribution of how it will come out is independent if you're on the left or on the right. So basically, if you inject the car here, then with probability 1 minus t, it will drop and come out here. So the counter here reads 1 minus t. On the right, it's a bit more complicated. If you inject the car, then with probability 1 minus t, it will fall. And then with probability 1 minus t, it will fall again. So you'll get the contribution 1 minus t squared. But then there is also the possibility that it will continue with probability t, and then a counter over here, it will drop with probability 1 minus t, so a counter placed here will read t times 1 minus t, and then you just go through, so you add another t times 1 minus t, and when you sum these two numbers, it's exactly this. Okay? And likewise, you can check, and in fact, this is exactly the same check. So again, you should yawn, because this is exactly the same check that the Bureau representation satisfies Reidemeister 3. But anyway, the conclusion is that overall traffic patterns are not changed by doing a Reidemeister 3 move. Namely, if you enter a Reidemeister 3 interchange, at the bottom, you'll exit at the top with the same distribution, be it left or right side. And the conclusion is that the green function is unchanged provided the car injection point and the traffic counters are away from the place of the move. Okay? But now I want to compare row 1 of the left with row 1 on the right. But row 1 was a sum, the interesting part of row 1 was a sum over all crossings of the green function evaluated near that crossing. So the only thing that can potentially change is the 3 R1 contributions, the 3 quadratics that involves specifically the crossings that are involved in the Reidemeister move. Okay? So, you know, suppose the labeling of the edges was 10, 11, 12, and then 20, 21, and 22. I just chose easy numbers. Basically, I have to show that the R1 contribution from this crossing plus the R1 contribution from that crossing plus the one from here is the same as this sum of R1s. But these R1s involve G in places that do change. But I have G rules that tell me that I can move the car injection point up, and I can also move the traffic counters up. I have rules that tells me how to do it. So all I have to do is I have to take this messy quadratic that I get from here, the messy quadratic that I get from here, apply to both of them the G rules, and with luck, I will get the same answer. Now, I have to say that I'm a lazy guy, so I would never do a calculation like that by hand, not when I have the tools. So basically, here is an implementation of the G rules. You can compare with your handout. It's the same as the formulas that I wrote before. The left-hand side is the sum of 3 R1s. I apply to it the G rules that apply to the left-hand side. The right-hand side is the sum of 3 R1s. I apply to it the G rules that apply to the right-hand side. I check if left-hand side is equal to right-hand side, simplify the answer, hit enter, the computer prints true, and therefore I know that it's an invariant. If you believe the computer, right. We checked pretty hard. I mean, this is, but in fact, the computation, I mean, it's just it's a paragraph of formulas. I'm just too lazy, okay? Anyway, likewise for Reidemeister 1. So in fact, in the case of Reidemeister 1, we already computed the matrix here, and I just copied it to here. So you take R1 minus the correction factor, and every place you see a green function, you replace it by the entries of this matrix. You hit enter. This time I didn't say simplify, so the computer prints out this ugly thing, and I just wanted to prove that I can do things by hand. This is handwritten. I computed it by hand. Reidemeister 1 works. Okay? And all the other things are proven the same way. So now, wearing my topology hat, I have no clue what's going on here. Okay? So the formula for R1, again, just to emphasize, this is one tiny box in my handout. It's a one-line formula. I have no idea where it comes from. I have no idea why one should look for such a formula. Once you look for such a formula, proving that it works is easy, but I have no idea where it's coming from. And my hope was that Cameron would tell me, but okay. And very, 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 very briefly, I want to tell you what actually took years and builds on the work of greats, how to see it from wearing a quantum algebra hat. So first of all, I spy a Heisenberg algebra. So you see, cars and traffic counters are more like Heisenberg thing than like duals, because if you can see it, because when you inject the car to the left of the counter, it counts 1. And if you inject it to the right, it counts 0. So basically, when you commute a car across a counter, you get a difference of 1. So there is some Heisenberg algebra hidden here. And where did it come from? And that's where I will be very, very sketchy. So for years now, Roland and I have been studying this algebra G sub epsilon, or sometimes called SL2 plus epsilon. And, well, here is the algebra. It's the algebra generated by y, b, a, and x, subject to these commutation relations. If you want to know where it comes from, so basically it's the following. So SL2 can be reconstructed from half of it, from the upper Borel, by adding to it the lower Borel. But unfortunately, you get the Cartan doubled, so you get a 4-dimensional algebra instead of a 2-dimensional algebra. Now, the lower Borel is the dual of the upper Borel. So in fact, SL2 can be reconstructed from the upper Borel, which is a Lie bialgebra. It's a Lie algebra whose dual is also an algebra, which means that it has a bracket and a co-bracket. But now, instead of reconstructing SL2, you multiply the co-bracket by epsilon. So it's kind of the upper Borel plus the lower Borel faded away. Okay? And you get a 4-dimensional algebra, and this is the 4-dimensional algebra written here. And at invertible epsilon, it's actually SL2 plus the Cartan got doubled, so it gets an additional central factor. And then all the quantization tools of Drinfeld, the Drinfeld double, work for this algebra. And you can quantize and you get a new algebra, QU, which is the associative algebra generated by the same generators and subject to some quantized relation as written here. And it comes free with an R matrix. So something that satisfies the Young-Baxter equation or Reidemeister 3, and it's written here. And so it has a so-called universal quantum invariant, and you can read about them more in the work of Ruth Lawrence and Tomotaro Otsuki. But the point is that as algebras, to compute the quantum invariant, you only need the algebra structure. You don't need the co-algebra structure. So as algebra, where's the mouse? QU is isomorphic to the universal enveloping algebra of SL2 epsilon. And the universal enveloping algebra has a representation, a faithful representation into a Heisenberg algebra, basically by studying some Verma modules. And so you can push the R matrix to some calligraphic R matrix, which lies in the Heisenberg algebra tensor itself. And the fortunate thing is that everything still makes sense. So, I mean, this is, so far we've done things related to SL2, but everything still makes sense when you set epsilon equals to 0. And when you set epsilon equals to 0, you can actually expand everything in powers of epsilon. And you get that the R matrix can be written as R0 plus 1 plus epsilon R1, where R0 has some explicit formula. And then when you expand the invariant in powers of epsilon, then basically this contribution, epsilon times R1, oh, I forgot to say that R1 is a quartic polynomial in P and X. So this contribution will toss in X's and P's on the knot in various places, and you'll have to commute them across R0 to some garbage bin at the top where you'll count everything. At the end, at the top, right, because the knot is vertical. So you'll have to commute everything across R0 to count it. And so you end up commuting P's, Porsches, cars, and X's, counters, across R0, and the commutation relations are written here, and that's exactly the Burau representation. So when all the dust settles, you get precisely our formulas for R1, for rho 1. But you also know that QU has all the other benefits of quantum algebra. So in particular, it's a quasi-triangular Hopf algebra, and this translates to the fact that rho 1 is homomorphic, though I will not tell you exactly how. Okay? And what do I have to say here? I forgot. I think it's just, oh, yeah. So of course, you could continue and expand and figure out what's rho 2 and what's rho k in general, and they all make sense, and they're still polynomial time to compute. And furthermore, the same game can be played not necessarily with SL2, but with any other semi-simple algebra. So rho 1 is far from being alone. And I think I want to end by, if this looks like insanity, so basically using such a huge hammer to explain something so simple, then it should look like an insanity. I mean, it's wrong. There should be a simple explanation. So homework to you is to explain rho 1 with no reference to quantum voodoo, and find for it a topology home, and it's even better if the home is a bit bigger so it can fit all of its neighbors. Okay? And I think I want to stop here. So thank you for suffering with me.
Dror, thank you very much for the formulae and the interpretations. I think now, if people want questions on the floor, I need to hand them this. If people online want questions, they unmute and ask.
Or if the questions are short, I'm happy to repeat them.
Thank you. I have a couple questions. So, first of all, I genuinely don't know what's known about this, but yeah, like if you assume like that P is not equal to NP, does the fact that this is computable in polynomial time place any limits on how strong of an invariant it can be?
I'm probably. Though I am not an expert, but well, it's still better than Homfli and Khovanov.
Yes, yeah.
And also, which are not polynomial time. And also, you know, our purpose is not just to separate knots, right? It's also everything that comes from the fact that it's homomorphic. So basically, it should have good formulas for knots of a fixed genus and for ribbon knots, and that I couldn't tell you about, but that's definitely a big part of our motivation.
Yeah, thank you. And the second question, right, so in this Lin Wang paper, they give a proof of the MMR conjecture, right? And there's also kind of a random walks interpretation of the Jones polynomial. So
it's very, very similar.
Okay. Yeah, I was wondering if there's kind of an analogous thing.
It's very similar, indeed.
Yeah.
So, I mean, well, the new stuff is not the invariant itself, but the fact that it's so simple and the fact that it's homomorphic, which I didn't really talk about.
Mm-hmm. Okay, Thank you.
Any,
I have a simple one, you can repeat it. Did you find a chiral knot with vanishing row 1?
Did we find a chiral knot? A chiral. Chiral knot with vanishing row 1. Ah. We didn't look. Okay. I mean, in principle, we've computed row 1 for, I think we stopped at 14 crossings. So it's a search, but we didn't.
I have a somewhat philosophical question about the numbers you showed, right? These simple knots up to 12 crossings.
Yeah.
And the image of the kind of number of elements in the image of various invariants.
Yeah.
And they all come very close to the number, right? To the total number of simple knots, but there are just some sort of smallish defects. But how is it, could you give a little bit of perspective on it? Is it like this difference is so small just because 12 is such a small number? Or like what's the expectation? Or do we have some expectation on how large the image should be? Or if you go to 120 crossings, the image will be very small in comparison to the total, or we don't know? Thank you.
I think we don't know, and basically because you cannot enumerate all the knots with 100 crossings, and if you take random knots with 100 crossings, they're likely to be very different from each other. So it will take a very long time until you'll find a place where your invariant fails to separate. So I don't think we really know, but we can speculate. And my speculation is that this really is just a low crossing number coincidence. So, for example, if you're taking a knot with 1,000 crossings, it's likely that somewhere you will be able to do a mutation. And then most of these invariants don't detect mutations. So yeah. So likely this is a small crossing number coincidence.
can I just come up on that one? What way does row 1 behave under mutation? So all the philosophy at the very end says that it's dominated by the Color-Jones polynomial, which does not detect mutation. So row 1 does not detect mutation. But row 1, and neither would row 2 or row 3 or row k in general. However, row k should have a cousin if you start with SL3. And it should still be polynomial time to compute. And then that one should detect mutation. Is that to do with the homomorphicity? Because when you're talking
no, all of them
SL3 and SL2 and doubling a thing taking a satellite isn't detected by mutation, but mutation can be detected by SL.
Yes, it's the same fact. Yes.
Okay, well, thank you very much, Dror. I think if we stop and thank Dror once more for leading us over the car.
Thank you.